Good afternoon again. Screen sharing has decided to restart, so we're looking good. Time to start chapter 4. There's no do now. We're just going to jump right into chapter 4. Before we get there, I want to let you know the things that are not going to be specifically covered in our live lecture that you're still responsible for. So please make sure that you watch the chapter 4 video that is already posted to YouTube, the pre-recorded one in the lecture series. The topics listed here are covered in that video. So you'll need to know more of the history of the development of the model of the atom. We'll talk a little bit about the plum pudding model as kind of the basis for our jumping point. And then when we start talking about the energy levels and sublevels and orbitals, I'm not going to talk about the shapes in today's lecture, but it is in the video, so you'll want to know those shapes. And that last part will make more sense as we get further into the lecture if you haven't had a chance to watch the recorded lecture for chapter 4. So make sure that you know these topics. When we come back next week and do chapter 5, the do now will be some multiple choice questions, and I'll make sure that a couple of them hit on these topics to make sure that we're all good. Anybody have any questions about kind of logistics for the course or anything like that? This would be a good time to ask it. Otherwise, let me know how you're doing, how you're feeling. Did you get hit bad by the storm? Let me know what's going on. Alrighty, then we'll just go for the gold. We're going to pick up in chapter 4 talking about the Rutherford model of the atom and how we got there. Ernest Rutherford was a student of J.J. Thomson. He learned from the best and then said, okay, I'm going to have my own lab. I'm going to have my own student, and I'm going to set up an experiment to test the theory that my mentor came up with. That theory was the plum pudding model, right? That describes what J.J. Thomson thinks an atom looks like. And he said that there's a sea of positive charge that we can call the pudding, and inside of that were the electrons. Those are the plums or the raisins. Electrons are very small, so this atom is largely empty space. Ernest Rutherford said, okay, if the plum pudding model is correct, then I should be able to throw some particles at an atom, and those particles should just go straight through, because there's nothing massive enough inside of an atom to deflect these particles. So if you think about if you're doing bumper cars, if there's no other cars in there, then you could just ride around. You can go from one end to the other, no problem. But if there's some kind of an obstacle, like another car, and you're trying to go from one end to the other, you're going to bump into it because those things are terrible with steering and they're designed to make you bump into each other. So those alpha particles, if there is something massive inside of the atom, it'll encounter it. So that's the thought behind this experiment. This is the setup. You have a source of alpha particles. You shoot them at a thin gold foil, which is why you'll see Rutherford's experiment known as the gold foil experiment. And if the plum pudding model is correct, all of the particles are going to come out the other end undeflected. But that's not what he saw. Most of the particles were undeflected, but some scattered at large angles. And that was a result he wasn't expecting. Since most of the particles pass through the foil, it's true that the atom is largely empty space. But he proposed that there must be an atomic nucleus. It's at the center, and it contains the atom's protons. Because of the massiveness of the nucleus, he also proposed some kind of neutral particle as part of the nucleus as well. When the alpha particles were deflected, they hit the nucleus. The majority of the mass of an atom is at that center, the protons and the neutrons. So someone else discovered the neutron, which then confirmed Rutherford's model of the atom, that there's a nucleus with a neutrally charged particles and positively charged particles called protons. So that's the Rutherford model and the history kind of the game-changing experiment that led to the Rutherford model with the atom having a nucleus. Any questions about that so far? Any questions about the experiment? You'll need to know kind of what is the experiment, what were the results, and what did it mean? So let me know of those three things. If you're like, okay, I know what that is, or I understand what I'm expected to know, let me know if you're ready to move on. All right, thank you. So this is just a summary of Rutherford's model. The protons are red, neutrons are blue, the electrons are super small, and they occupy the space outside of the nucleus. This chart of subatomic particles will be really handy to you if you're a person that likes to have charts to summarize information. Each of the subatomic particles that you'll need to know are in this table: electron, proton, and neutron. Along with the symbols, I use these symbols when I'm, teaching, if we're in office hours. So you'll need to know these symbols. You'll also need it for the exam and for your homework. The location of each of these particles is listed, and their relative charge. Electrons are negatively charged, protons are positive, neutrons are neutral. It's not rocket science. The final column is the relative mass. I don't require you to memorize this. So you don't need to memorize that an electron is 1/1836 of the mass of a proton. I just want you to know that the electron is tiny and the proton and the neutron are the same mass. That's all you need to know. Everybody good on this? You probably heard this before. This isn't really new information. So let me know if we can move on. Okay. Atomic notation. Each element has its own number of protons. So if you're carbon, part of the reason why you're carbon and nothing else is because you have 6 protons. The number of protons in the nucleus is called the atomic number. So let's start introducing some of that nomenclature in the symbols. The atomic number is equal to the number of protons. Remember, that's the P with the plus sign. When you add up the protons plus the neutrons, you get the mass number, which we use an A to symbolize. So that tells you how many particles you have in the nucleus. That's the protons plus the neutrons. If we want to represent an element, we use the symbol of the element, and then we can put the mass number at the top left and the atomic number underneath it. To go along with our carbon example, carbon has 6 protons and 6 neutrons. If I wanted to write that using atomic notation, what am I putting for the mass number? The mass number is the protons plus the neutrons. Right, it would be 12. What's my atomic number? Six. That's how you would represent carbon that has 6 protons and 6 neutrons. Now we haven't addressed electrons yet. In a neutral atom, meaning it doesn't have an overall charge, you're going to have the same number of protons as you do electrons. The number of protons is equal to the number of electrons. Remember that we've got positive charge from the protons, negative charge from the electrons. If you have the same number, then you have equal but opposite charges that cancel out and give you a neutral atom. Let me know if you're still rocking with me. Let me know if this makes sense. Great, thank you. One more concept and then we're going to do some practice. One of the reasons why we need to use atomic notation is because of the existence of isotopes. If you've got a group of atoms that are all the same element but have a different number of neutrons, those are isotopes. One example would be if you have magnesium, there are actually 3 isotopes of magnesium. Magnesium 24, magnesium 25, and magnesium 26. This is another way to represent an isotope, using the element name or the symbol with a dash, and then writing the mass number. They all have 12 protons, but the number of neutrons is different. we've got 12 neutrons for magnesium 24, 13 for magnesium 25, and 14 for magnesium 26. Same number of protons, different number of neutrons. Also of note, when we're talking about the mass number, mass numbers do not appear on the periodic table. The mass number is a whole number. So is the atomic number. You're counting the number of particles, so it should be whole. You can't have half a neutron. It doesn't make sense. However, on the periodic table, you will see the atomic number. And its location is usually above the symbol. So make sure that you know that distinction. With that, we're going to do some practice. I'll give you 5 minutes to fill in this chart. There's missing information in each row. You'll need to identify which element is represented in each row and write that element using atomic notation. Using all of the information about how the atomic number, mass number, and everything else are related, you can fill in each of these blank spaces in each row. Again, 5 minutes. There's a periodic table posted in course content. I think I sent out an announcement this morning asking you to have it with you, either print it out or just pull it up if you don't have access to a printer. We're going to be referring to a periodic table kind of throughout, especially when we get towards the end of class when we're talking about electron configurations. So take 5 minutes. I'm giving you 5 minutes so that if you didn't pull up the periodic table, you still can, and then fill in the chart. So I'll check back in 5 minutes. Then let's go over it. First row, we know the atomic number and the number of neutrons. Since we know the atomic number, that means we know the number of protons, and we can fill that in. The mass number is protons plus neutrons. 9 plus 10 gives us 19. The number of electrons is the same as the number of protons. That will be 9. When you're looking it up on the periodic table, look for the atomic number 9. So you'll find the element that has a 9 above its symbol. Did anybody figure out which element it is? You could put it in the chat. Yes, it's fluorine. To write that in atomic notation, you're going to put the mass number up top and the atomic number down below. Second row, we've got the mass number and the number of protons. If we know that we can add the protons and neutrons together to get the mass number, then we can take the mass number, A, and subtract the protons to get the number of neutrons. 31 minus 15 gives you 16 neutrons. The number of electrons is always equal to the number of protons in a neutral atom. And the atomic number is the number of protons. Yes, you have a question? Go for it. Oh, no problem. Happens all the time. So for this one, our atomic number is 15. Which element is that? It's phosphorus. The symbol for that is P. And to write it in atomic notation, you put the 31 up top, the 15 down below. You will need to put elements in proper atomic notation on mastering chemistry. So make sure you know which number goes where. Now we have the last one. The atomic number is 28, and the number of neutrons is 31. If we know the atomic number, automatically we can fill in the number of protons and the number of electrons for a neutral atom. All you have to do now is figure out the mass number, which is adding the protons plus the neutrons. When you add those two together, you get 59. What's our element for this row? It's nickel. And there is atomic notation. Any questions on this? Okay. I'll put some practice up in the Chapter 4 folder. It'll be called Additional Practice. It's not for credit. There's no chapter check-in for Chapter 4 because y'all have a lot of mastering due this weekend. But I'll put that up there so you can have some extra practice if you want it. Moving right along. Now we need to talk about atomic mass. If you're looking at a periodic table, let's say you're looking at carbon, we said that the atomic number would be up top. The one that I posted, it's like up top and to the side, but it's usually above the element. Below the element symbol, you'll see a decimal number. That decimal number is the atomic mass. The atomic mass is always a decimal number. It's very rarely just a plain old whole number on a periodic table. There's usually some decimal places. What's different about the atomic mass is that it's a weighted average. This means that it takes into account all of the known isotopes of an element and the percent abundance. So if we have our magnesium example, where we've got magnesium 24, magnesium 25, and magnesium 26, and let's say that their masses were 24, 25, and 26. An atomic mass is measured in atomic mass units. So that's AMU. In a normal average, you would just take 24 plus 25 plus 26 and divide by 3. If you did that this time, it would be wrong. That's not a weighted average. We have to take into account how much of the magnesium in the earth is 24, 25, or 26. The majority of it is magnesium 24. And the rest, I don't remember how it's broken up, but so this is not accurate. I know that there's more magnesium 24. My brain's a little fuzzy on the percentages. But if we take into account the percent abundance as a weighted average, then what you'll see when we calculate it, and I'll show you how to do that on the next slide, that the atomic mass is going to be closest to magnesium 24, the mass, because most of the isotopes in magnesium are magnesium 24. So what does that mean? It's kind of abstract. What we're going to do first is go through the example that I did in the video. So if you watch the video, you can tune out for a couple minutes. If you didn't, watch along so that you understand how to calculate a weighted average. Gallium's got two isotopes, gallium-69, and I'll highlight the information for that in yellow. The mass is 68.926 atomic mass units, and it has an abundance of 60.11%. The second isotope is gallium-71. I'll highlight that information in green. The mass of that isotope, 70.925 AMU, and the abundance is 39.89%. We need to figure out the average atomic mass of gallium. Average atomic mass is the same thing as saying we want the weighted average. Whenever you're doing an atomic mass question like this, where you get percent abundance and you get the mass of each isotope, you're calculating a weighted average. Don't be tempted to do a regular average. To organize this information, because you may get more than just two isotopes in a problem, I make a table. Those are our two isotopes. Those are the masses from the problem. And the percent abundance. There's one more column that I like to add, and that's the abundance expressed as a decimal. You take that percentage and divide by 100. That will give you the decimal. So this is my table. Now I need to put together my actual equation. What am I putting in the calculator? Well, I told you that you have to take into account the abundance as well as the atomic mass. We have to do that for each of the isotopes. You take that percent abundance as a decimal and multiply that by the atomic mass. I like the table because it helps you organize which atomic mass goes with which abundance. So that's the contribution to the average atomic mass from gallium-64. To that, we need to add on what gallium-71 contributes. So to show you on the table, where we got our values from. Now you need to put this into your calculator. Try it out and see what you get. And I hear somebody's mic on. I don't know if you mean it to be on. Once you have an answer, you can put it in the chat. I want you to try putting this in your calculator to make sure that you know what you're doing. Yeah, your calculator is going to tell you 69.7234, bunch of numbers. We're going to look at the problem to see how many sig figs we need. So all of our percent abundances are 4 sig figs, and the masses are 5 sig figs. We're going to go with 4 sig figs here. So when you're doing your mastering homework, they may just tell you round to the hundredths place or round to the thousandths place or that kind of thing, or tell you how many significant figures. Just make sure you pay attention to that. Can we move on to another problem? I have one for you guys to try. Okay. So you've got element X. It occurs naturally as X6 and X7, and there are the masses. Calculate the atomic mass given that the natural abundance of X7 is 92.5%. I'll give you 3 minutes to solve this problem, then I'll check in with you and go over it. Okay, I'm going to jump in here and start solving the problem. If you are not finished, you can keep working if you want to. If you got stuck, I'll help you get unstuck. Start by making that table. We know the abundance of X7 is 92.5%. And we can write that as a decimal. Just have to divide by 100. What's the percent abundance for X6? If you got stuck here, let me know that you got stuck. One thing that we know about percentages is that it should always add up to 100%. So if you're missing one of the abundances, then you can take all the rest of them and subtract them from 100. And that will give you the missing abundance. So you should get 7.5%. Yeah, no problem. So the green is what we had to fill in ourselves. You will see a problem like that. Definitely on the homework, definitely on the exam. So make sure you understand that concept. Percent abundance has to total 100%. Use that to your advantage. Now we've got all the pieces. We can put the whole thing together. We've got the contribution from X6 and the contribution from X7. Let me know what you get in your calculator. So you should get 6.94. There's a bunch of other digits too, but we can only use 3 sig figs. Everybody good with this one? All right. We've got one more. This is a conceptual question. I give this type of a question every year. And every year, even though I tell you exactly how to do it, still have people do it wrong. I want everybody to get it this time. Given the only naturally occurring isotope of fluorine is F19, determine its mass from the periodic table. If it says that it's the only naturally occurring isotope, that means that there is only one isotope. We said that the atomic mass that's on the periodic table is the average atomic mass of all the isotopes. If there's only one isotope, the mass on the periodic table is the mass of that isotope. So in this case, we've got F19, fluorine. You look at the periodic table and you see what it says. The periodic table that I posted will say this. Usually has 3 decimal places. Other periodic tables might say 19.00. That's the answer. It's simply look at the periodic table, see what it says. That's the mass. So if I told you any other element, say sulfur, which is not true, but sulfur has only one naturally occurring isotope. Determine its mass from the periodic table. What would you tell me? Yeah. So sulfur is S. Yeah. So if you look at that periodic table, sulfur is 32.066. That would be the answer. This is the only time when you do this for an atomic mass question. It's not a trick. It is as simple as it seems. So make sure you get this one right on the exam. You will see one like this. Questions about this? Good. Now we're going to switch gears a little bit so we can take a 5-minute break, shake your brain out. When we come back, we're going to be talking about kind of abstract stuff, talking about waves and electron configurations and how atoms, the space is arranged. So get ready. Take 5 minutes. We'll break till 3:01. So I'll see you in 5. All right. Had an extra minute there, but it is what it is. We're going to get started again. And it's almost like a totally different chapter, but it's not. We're going to start with going over the radiant energy spectrum. You've probably seen this before if you've taken physics. This is a continuous or an uninterrupted spectrum. We've got short wavelengths on the left, long wavelengths on the right. We'll talk about the characteristics associated with each and what you'll need to know. Then we'll do some practice problems. Let's say I have a wave. The distance from the two peaks, two continuous peaks, or not continuous, my words are struggling today, consecutive. So two peaks in a row. That's going to be your wavelength. The symbol for that is a lambda. It can be from peak to peak or from trough to trough. The number of cycles that you can go through, meaning how many peak to peaks or trough to troughs you can do in 1 second, is the frequency. For short wavelengths that are high energy, there's also a high frequency associated with that. With long wavelengths that are low energy, you have a low frequency. What we have down at the bottom is from the highest energy, highest frequency, shortest wavelengths, all the way down to the longest, lowest energy, lowest frequency. So cosmic rays, gamma rays, those are things from the solar system. Okay. Gamma rays you can also get from nuclear radiation. X-rays you've encountered if you've gone to the dentist and you've had those dental X-rays. I think you get those like every other year or something like that. If you've ever broken a bone or thought you've broken a bone, then you may have had an X-ray as well. Ultraviolet light, that's that UV light. That's why we wear sunscreen when we're outside, even if you have melanin in your skin, because UV will attack your DNA, and that's bad. It's also part of the reason why we wear sunglasses. It protects your eyes. So again, we're going from the highest frequency all the way down to the lowest. We just went through ultraviolet light, visible light, that's what we see. It's all the colors of the rainbow. I learned the rainbow in order from lowest to highest frequency. Roy G. Biv. We got violet, indigo, blue, green, yellow, orange, and red. The order matters here because you need to be able to compare one wavelength of light to another to say which is higher in energy or lower in frequency, things of that nature. Then there's infrared, microwaves, TV, and radio. So those are on the lower end of the spectrum. You don't need to know specific wavelengths, as in numbers of nanometers. Just know the relative order of these different rays. Everybody good on what you need to know? The next slide is going to be practice problems. I'll have this this diagram up. But are we ready to do some practice problems with this? Let's do it. So we can just do this as a class. There's no need to write it down. You can just put it in the chat. We're going to consider blue light and yellow light. So if your answer is blue, you can put a B. Yellow, you put a Y. I've got your reference chart down at the bottom, which you will not get for your exam. So you'll need to know this. Of these two, blue light and yellow light, which one has a longer wavelength? You could put a B for blue or a Y for yellow. It's going to be yellow. Yellow has a longer wavelength. And you can even see it here because I have the nanometers associated with the wavelengths for the colors. So yellow is close to the 600 range, and blue is more of the 500-ish range. So 600 nanometers is definitely longer. Which one has higher energy, blue or yellow? Blue. Since the yellow light has the longer wavelength, blue is the shorter one. Shorter wavelength is associated with higher energy. Which one has a higher frequency? It's going to be blue light again. Higher energy, higher frequency, shorter wavelength. Now we'll do number 2. We've got infrared light and X-rays. You can put I or X. Which one has a longer wavelength? That infrared light. Which one's higher energy? And just like last time, it's going to be the X-rays that also have a higher frequency. These are the types of questions you'll get on the exam. So if these were easy, then it'll be smooth sailing for you on this part. We ready to move on? Let's keep pushing. So we talked about that, so we could talk more about the atom. The next model of the atom that we'll talk about is the Bohr model. And what he speculated was that electrons orbit around the nucleus in fixed energy levels. Now, he didn't get the fixed part right, and we'll talk about that in a little bit. But the energy levels, he absolutely did. What he said was that electrons are only found in specific energy levels and nowhere else, which means that the energy levels are quantized. So if I have an energy level here, and that black band is my energy level, and then I have another black band here for n equals 2, in between, I'm not going to have any electrons here. That space is kind of no man's land. You'll find electrons in this band, in this band, but you won't find it in between. So it's kind of like when you're going up or down the stairs. You can't really go up or down half a stair. It's either you're on one step or you're on the one below it or above it. No in between. That concept is what we mean when we say that the energy levels are quantized. There's a specific energy level associated with each one. How did we get there? Well, one of the pieces of evidence is a line spectrum. When you put an element into a tube and you heat it up so that it becomes a gas, or you take a gas like hydrogen and you heat it up, you're going to excite all the electrons in that hydrogen or whatever element. Once you stop exciting that gas, the electrons are going to release or emit light. That light is filtered through a slit, which then goes through a prism and separates into the different colors. When you do that for any element, you'll see an emission line spectrum. You'll see discrete bands of color. Now remember, on the other slide we were looking at visible light spectrum, and that whole radiant energy spectrum, it's continuous. But these emission line spectra are not. You've got discrete bands of different colors, so you're looking at specific energy levels being released from these electrons as they go from an excited state back down to a less excited or ground state. I should go back and make sure that everybody's with me here. So are we good on the idea of specific energy levels for electrons, and that the evidence for that is when electrons get excited and release energy, they're releasing energy in these specific numbered packets. So violet light has a specific energy. Blue-green light has a specific energy. Red light has a specific energy, and nothing in between. So let me know if you follow me or if you need me to re-explain something. Oh, don't let it be crickets. If you need me to go over something again, let me know. If you're ready to move on, let me know. Okay. One more thing about energy levels. When electrons move to a higher energy level, they're going to absorb energy. So if we break up this slide into two halves, this is the electrons going to a higher energy level. To do that, they have to absorb energy. And the amount of energy needs to be the right amount to get it all the way up to that specific energy level. So if you think about going up the stairs, if you don't lift your foot high enough, you're going to trip. You have to lift your foot up high enough so that you can actually put it on the next stair. If you don't lift it high enough, then you're not getting to that next level. There is no in between. You can't go up 3/4 of a stair. You're either going up the whole stair or you're staying on the stair that you're at. It's the same thing with energy levels. If the electron doesn't absorb enough energy to go from that lower energy state to a higher energy state, it's not going anywhere. If you want to jump up to an even higher energy state, say that's the equivalent of skipping over 2 or 3 stairs, it's the same deal. You have to have enough energy to move from, say, level 1 to level 3. If your legs aren't long enough, or if you're too tired, you're not going to be able to skip over 2 or 3 stairs as you're going up the stairs. Bad things might happen. On the opposite side of that red line, we've got electrons going from a high energy state back down to a low energy state. When this happens, your electrons are emitting a photon. A photon is just a particle of light. So those emission line spectra we were talking about just a slide ago, that's what we're talking about. This is what you would see on an emission line spectrum. If you're going from a really high energy, we'll call this one level 2, level 1, and this super high one, level 3. If you're dropping from 2 down to 1, you're going to emit some energy as a photon. If you're dropping from 3 down to 1, it's going to be a higher energy photon because the drop is more drastic. So in the picture, you see red light for the first example and green light for the other. Red light is lower energy than green. So the colors were on purpose. Let me know if you're with me, if you understand the idea of moving from high to low and low to high, and what that means for energy. Well, let me ask you a question. If I have an electron that is at energy level 7, and it then drops down to energy level 4, will it absorb a photon or will it emit a photon? So you could put A for absorb, E for emit. What's going to happen if that electron is going from a level 7 to a level 4? It's going to emit. Good. Let's say that I had 1,000 electrons at that level, and they all drop down to level 4. That means that I'm going to emit 1,000 photons. So each electron will emit 1 photon. Same is true for absorbing energy. That electron is going to absorb 1 photon, and it's either going to be enough energy to jump up a level or it's not. Any questions here? Seems like you guys get it. For the sake of time, I'll just move on. Now we're going to get into energy levels and sublevels. we're going to talk some more detail about what these energy levels are that the electrons are moving between. Think about energy levels as like a parking garage. You'll see energy levels called principal quantum number. You'll also see the abbreviation N. In a parking garage or parking deck, whatever you call it, you've got multiple levels. And in those big parking garages, sometimes you have 1A and 1B, you know? So it's still level 1, but it's different sections to make it easier to find your car. The energy level is that main level. So let's say, level 1, 2, 3, 4. The sub-levels would be like 1A or 1B. Which half of the parking deck are you on? In terms of energy levels, we've got 4 sub-levels. S, P, D, and F. The first energy level has 1 sub-level, and that's 1s. The second energy level, so this is n equals 1, it's got 1s. The second energy level is n equals 2, and that's got the 2s and the 2p. The third energy level, n equals 3, has 3 sublevels, S, P, and D. If this is the center where the nucleus is, as you increase n, go from n equals 1 over here to n equals 3 over here, the electrons have more energy so they can exist farther and farther away from the nucleus. So when you increase that energy level, the electrons are farther away from the nucleus. Keep that idea kind of tucked away. It's going to come back in chapter 5 when we talk about periodic trends. This is the reason for some of the periodic trends that we're going to talk about. So make sure that's something you understand. Do we get the difference between energy levels and sublevels? I hope the parking deck example or analogy helps you. So do we get the difference there? Okay. So let's keep going. We've got one more term to add to this. We've got to talk about orbitals. Now we're talking about the quantum mechanical model of the atom, which is where we are now. Quantum coming from quantized. We have energy level, and that's like the entire floor of that parking deck. We've got the sub-level, the different parts of the deck so you can find your car, 1A, 1B, 1C. Then we've got orbitals. That would be like the parking spot. So you know where you parked. You have a pretty high probability of finding your vehicle there. If it's not there, you need to call AAA, or maybe somebody had you towed because you parked there when you shouldn't have. But in most circumstances, the parking spot that you parked in is where you'll find your vehicle. That's where you have the highest probability of finding it. It's the same with an orbital. An orbital is the region of space where there's a high probability of finding an electron. And in terms of size, it's the smallest. The higher the energy of an orbital, the larger its size. Let's say I've got 3 main energy levels, 1, 2, and 3. For n equals 1, I just have the S sublevel. N equals 2, I've got 2p and 2s. I should write that in the proper order, just for consistency. 2s and 2p. For n equals 3, there's 3s, 3p, and 3d. If I were to compare 1s versus 2s versus 3s, that would be a comparison. The center is the nucleus, and the distance from the nucleus to the outer edge keeps getting bigger. What we also need to talk about here is the number of orbitals in each sublevel. For the S sublevel, there's 1 orbital. The P sublevel, there's 3 orbitals. The D has 5. And F has 7. You'll need to know the shape of S, P, and D orbitals. I go over that in the video. That's just something you have to memorize. Not really a concept there. Don't worry about F. But make sure you know the shapes of the S, P, and D orbitals. Everybody with me so far? And we're building up here so that we can write electron configurations. So we'll do that together in a couple more slides. Now we'll talk about the number of electrons that we can fit in each of these energy levels and what that means for the total number of electrons. In the first energy level, we've got the 1s sublevel, and that's it. The S sublevel, no matter where you see it, 1s, 2s, 5s, it always has 1 orbital. Each orbital holds a maximum of 2 electrons. So if we're figuring out how many electrons we can fit in each sublevel, we take the number of orbitals and multiply by 2. Here that gives us 2 electrons in the 1s. Now we're looking at n equals 2. We've got 2 sublevels here, the S and the p. You'll need to know how many orbitals are in the s versus the p versus the d and the f. S sublevel means one orbital. So you get 2 electrons in that sublevel. Can only fit 2 cars. 2p, the p sublevel has 3 orbitals. If each of those holds 2 electrons, then we can get 6 electrons in the 2p. So the total that we can hold in the 2 energy level would be 2 plus 6 for 8 electrons. But what if we had an element that had both the n equals 1 and the n equals 2 full of electrons? Then that means we've got a total of 10 electrons. We've got the 1s filled, the 2s filled, and the 2p filled. Now we're starting to sound like an electron configuration. But let's talk through one more. Just for your reference. We've got 3s, so that's 1 orbital. The p's we've already done. The d has 5 orbitals. If I have an element that has energy level 1, 2, and 3 completely full, what's the total number of electrons that that element has? If you're stuck or you're lost, let me know. But how many electrons total would this element have? So what we did here to figure out the 10 was we took all of the electrons in n equals 1, which was 2, and all of the electrons in n equals 2. We had the 2 in the 2s and the 6 in the 2p. That was 8. So we totaled that up to get 10. Now we're adding on the 3rd energy level. If we just total up the electrons in n equals 3, we've got 2 in the s, 6 in the p, and 10 in the d, for a total of 18. If we have all 3 energy levels filled, we're adding n equals 1 plus the n equal 2 electrons plus the n equals 3 electrons. So it would be 2 plus the 8 plus the 18. So we've got 28 electrons here. Does that make more sense? with that said, let's fill in this last one. Let's say that we have n equals 1 full, n equals 2, n equals 3, and n equals 4. What's the total number of electrons that this element would have? Yes. We're taking the 2 from the 1s plus the 8 from the energy level 2. So that's 2s and 2p. And then we have 18 electrons from n equals 3, and that's the 3s, 3p, and 3d. And then we're adding on all of the electrons in n equals 4. Sure, I can explain it again. For 28, we said if I have an element that has all of these sublevels full in n equals 1, n equals 2, and n equals 3, I'm totaling up all of the electrons that I can hold in each of these sublevels. So in the 1s, I can hold 2. Let me switch colors here. In the 1s, I can hold 2. In the 2s, I can hold another 2. In the 2p, I can hold 6. That totals 8. So that's my n equals 2. N equals 3, I've got the S, P, and D sublevels. All of those 3 combined give me 18 electrons in the n equals 3, the main energy level. So you can think about it as 18 parking spots. And if they're all full, I've got 18 cars. If all of the slots available in the sublevels are full for n equals 3, that means I'm adding on another 18 electrons. When I add up how many cars are in the garage, I'm adding the cars in the first floor, the second floor, and the third floor. Same with the electrons. I'm adding the 2 plus the 8 plus the 18, and that gives me 28 electrons. Does that help? Okay. I told y'all this is really abstract. It's one of those things that you just have to practice. Final step before we start writing electron configurations. If you have a printed periodic table or you have a tablet that you can draw on this periodic table, this would be the time to do it. If you want to do it afterwards and break out the color pencils and the markers as stress relief, that's fine too. Or you can just print out this slide from the lecture notes after I post it, slap it in your notebook. Totally up to you. We can break up the periodic table into different blocks. I'm going to use different colors here. In black, we have what's called the S block. All of the elements in the S block are filling an S orbital. Then we've got the P block. Put that in purple. The P block is filling a P orbital. The D block is there in the middle. Elements in this block are filling a d orbital. And the final one is the F block. Now it's always drawn below the periodic table, but notice these asterisks here. What it means is once you get to barium, which is element 56, then you go on down here to this row. Same thing with after radium. You go down there and read that row. Then you come back up and keep going. This is the F block. Let me write that. So you're filling an F orbital there. The last piece that I'm going to add to this table is the different energy levels. There are 7 rows on the periodic table. Each of those rows stands for an energy level. There's all the S's. All of the P's. All of the D's. And all of the F's. To complete our cheat sheet, which you will not be able to use on the exam, but you can recreate it if you practice making it, is you can write out the full order so that you can literally know how to fill the electron energy sublevels from lowest energy to highest energy. I'm going to write that out for you now. I also did it in the YouTube video that's already posted. You literally walk across the periodic table and read it off. You always start here in this top left corner with hydrogen, right? N equals 1. That's in the 1s. So you fill that first. Then you drop down to N equals 2. You fill the 2s. Then you go across to the 2p. Drop down again to N equals 3. 3s, 3p. Level 4, 4s, 3d. So that's out of number order, but in energy, this is increasing order. 3d is a little bit higher in energy than 4s. Then you fill the 4p. It's the same pattern for N equals 5. And I think somebody's mic is on. So check your mic. We fill the 5s, the 4d, then the 5p. The pattern with the F's is that you fill the S. So we've got 6s, 4F, 5D, and then you fill the 6P. Same pattern again for the last row. 7S, 5F, 6D, then 7P. With this order, you can literally write any electron configuration for any element on the periodic table. If you don't have this down in your notes, make sure you get it there, either now or after I post it. You can print it out and slap it in your notebook. But this slide is like liquid gold. You're going to make another slide like this for chapter 5 with all of the trends and things on it. And between those two periodic tables, that will summarize all of those chapters. Let me know if you're ready and I can move on, because we can start doing some examples together. So let me know if you're ready. We are very quiet today. All right. Thank you. So in the video that I already posted, I put up 2 questions that we were gonna go over in class. So if you watched the video and you tried it on your own, you can compare your notes with what we do in class. If you didn't watch the video or you just didn't try it, then you can try it now if you want to, or just hang on and watch me do it. We've got to write the electron configuration for a neutral atom of zinc. You find zinc on your periodic table. The atomic number is 30. That means 30 protons and 30 electrons for a neutral atom. We've got to write a configuration that has a total of 30 electrons. I will label these. The one piece of information that's missing from our order is how to show how many electrons you have in each sublevel. Since our element of interest is in the 3D, that means that everything that comes before it is going to be full. So we'll write the maximum number of electrons that we can hold all the way up through 4s. Then we'll count to see how many of the 3D electrons we have. Starting with n equals 1, we've got the 1s, and it's got 2 electrons in it. That superscript tells you number of electrons. When you total up all of the superscripts in your electron configuration, that should equal the number of electrons that you're looking for. So we're starting with 2. Then we move on to n equals 2. We fill the 2s next. How many electrons can we fit in the s sublevel? Yes, we can fit 2. Whenever you see S, you fit 2. Now we've got 4. That's a far cry from 30. We fill the 2p. There's 3 p orbitals, and each of them can hold 2 electrons for a total of 6 electrons. Now we filled 1s, 2s, and 2p. We've got 10 electrons total. We're looking for another 20. We move on to n equals 3. This is the third row. Fill the 3s. It can only hold another 2 electrons. So now we're at 12. We fill the 3p and add on another 6 electrons. Now we're at 18. N equals 4. This is the row that zinc lives in, so we'll slow down and be a little bit more careful. We know the 4s is full, so that's another 2. Now we come to the D block, and that's where zinc is, so we count. That's 10. So zinc has a full D sublevel. And when you add up all of those superscripts, it gives you 30, which is the number of electrons zinc has. Do you think that you can try one of these on your own, or do you want me to do another example? Let's do another one. This time we'll do one that's even bigger. We need to write the configuration for neodymium, just all the way down here in the F block. I'll do all the labeling, and I do this on purpose so that you can get used to it. I would recommend that you draw this out for yourself and draw it out a few times so that it becomes natural and you almost don't need to draw it out anymore. You can just see it on the periodic table. Now, neodymium is way down there in the F block. It's going to have 60 electrons in that neutral atom. Everything that comes before 4F on that order of increasing energy for the sublevels is going to be full. And this is one of the elements that falls in this weird underneath the periodic table. So don't forget that when you're doing this type for your homework or for the exam. You start with the very top, n equals 1. You fill that 1s with 2 electrons. There's nothing else to fill, so we move on to n equals 2. We've got the 2s, which can hold 2 electrons, and the 2p, which can hold 6 electrons. Still nowhere close to neodymium. N equals 3. We fill the 3s with 2 electrons. We walk over to the 3p, and there's 6 there. We keep moving with n equals 4. We fill the 4s with 2 electrons, the 3d with 10, and the 4p with 6. So I literally just read off each of these in order from left to right. N equals 5 is the same thing. 5s, 2 electrons. 4d, 10 electrons. 5p, 6 electrons. Finally get to N equals 6. This is the row that neodymium lives on. We fill the 6s. Then we have to go down to the F block. That's where neodymium lives. We're on his street. So we count the number of houses. 1, 2, 3, 4. If you total all of those up, it will give you 60 electrons. How do we feel now? Does talking it through a second time even longer help? Okay. Now I want you to try one on your own. Won't be as long as this. I want you to write the configuration for a neutral atom of iron. I'll do a little labeling for you. Walk it through and see if you can write that configuration for iron. I'll give you 2 minutes and then I'll check in. All right. So I'll walk this one through for y'all too. We're trying to write a configuration for iron. Iron's got 26 electrons. We know that because the atomic number is 26, which tells us the number of protons. And in a neutral atom, protons, the number of protons is equal to the number of electrons. We always start with the lowest energy, which is the 1s. It's going to be full because iron lives in 3D. So we're not even on iron's street yet. Okay, so that's N equals 1. N equals 2, we've got 2s and 2p. The 2s holds 2 electrons. The 2p holds 6. We go to N equals 3, and we fill the 3s. And we fill the 3p. N equals 4. That's the street that iron lives on. 4s2 we fill. Once we get to 3d, we start counting houses. 1, 2, 3, 4, 5, 6. 3d, 6. If you total all those superscripts up, it will equal 26. That's how you can check your math and make sure that you did everything right. How did we do with this one? Do we feel a little bit better? About the same? Meh? Okay. I've got one more question for you. This time I want you to figure out which element corresponds to the electron configuration that I have listed here. I'm not going to label the periodic table this time. I'll give you 2 minutes to figure it out, and then I'll show you 2 ways that you can figure out the answer to this problem. I'll check back in 2 minutes. If you have an answer, you can put it in the chat. If you don't feel confident, or you're like, bro, I'm lost, then I'll talk it through for you. Yeah, it's fluorine. So, 2 ways to do this. The easy way and the less easy way. We'll start with the less easy way first. You can walk and count it out. 1s2, that would get you to helium. 2s2 would get you to beryllium. 2p5, 1, 2, 3, 4, 5, would get you to fluorine. That's the less easy way. Still easy, just less easy. The easier way is to total up your electrons. That's 9 electrons, and we're talking about neutral atoms here. So you're looking for something that's got a 9 for its atomic number, and that's fluorine. Either way you think about it, you get the same answer. So I'm glad y'all got it. That makes me happy. Any questions here? I'm going to guess no, because the folks that have been participating, y'all got it. And if you haven't been participating, hopefully you're soaking it in. So, reminders. Office hours already happened. So, if you missed that, I'm sorry. But don't forget that Tuesdays from 11:30 to 1, so pretty much before this class, I have office hours. If you need time outside of that, send me a message using course messages and set up a time. If you don't remember how to use course messages, go to the notes from the first lecture, the PDF, the live lecture, and look at that. It'll help you. You've got Mastering Chemistry due for chapters 3 and 4 this Sunday. So I gave you a break last weekend so you didn't have to get chapter 3 done, but I strongly encouraged you to work on it. The chickens are coming home to roost, so don't wait until Sunday at 8 o'clock to start your homework. You need to do chapters 3 and 4. They're due Sunday, February 28th, 11:59 p.m. Your second exam will cover chapters 3 and 4. It will be available March 3rd. That is next week. We'll do exam review in our class before we start chapter 5. Like I said at the beginning, I'll make sure to include some questions that touch on the topics in chapter 4 that we didn't cover specifically in class. Once we do that, we'll cover chapter 5 and keep moving with class. It's going to be a multiple choice exam primarily. There's really not much math, so it's just multiple choice, maybe fill in the blank, true, false, that kind of thing. I've started grading exams. I'm almost finished with one section of Chem 103. Then I'll start grading yours. So once I grade it, then you'll be able to look at the exam and you should be able to see what you got wrong. If you included your work for the math problems, then you may see some partial credit there. If you did not, even if your answer was really close, you don't get any points because I don't have any work for you. So, that's all I have for you. That is chapter 4. This is chapter 4 and chapter 5 go together. So even though our exam is on chapters 3 and 4, you really need to keep chapter 4 fresh in your mind when we're going over Chapter 5. I don't have anything else for you. If you have questions, feel free to ask. Otherwise, go enjoy the rest of your afternoon.